Hello everybody, today I want to explain about the star clusters. Let me share my screen. Initial mass function. The initial mass function theta m, often called present-day mass function or PDMF, is defined as dn is equal to theta m dm. dn is the number of all stars per cubic parsec on the main sequence with a mass between m and m plus dm. But we observe not the masses of stars, but their magnitudes, relative and absolute, or luminosity. So we have to define the luminosity function and transform it into the initial mass function. Here you see in each row, mv plus dm, as we selected them, there is a mixture of main sequence and involved objects for the initial mass function. We need the main sequence only, not the involved objects. Here is a color absolute magnitude diagram. These are evolved stars, and these are main sequence stars. For example, when we want to know the initial mass function of this star, we should know that it is from, at first, it was from which region or where. Luminosity function. The luminosity function, or psi mv, is defined as dn is equal to minus psi mv dmv. dn is the number of all stars per cubic parsec on the main sequence with an absolute magnitude between mv and mv plus dmv. The transformation to the initial mass function is given as theta m. The second term is the derivation of the mass luminosity function, MV, this one. It is depending on the age T, metallicity Z, and rotation V root or rotation. MV is equal to M MV and Z metallicity and T age and V rotation. Here you see the color magnitude diagram, and we want to know with which masses are these giants born. We follow the isochrone. We should have the isochrone to see how the stars were. Correction of the observations. We have to correct the complete observations for the evolved objects. There are three possibilities. 1. Take a statistical sample with a well-known luminosity function, clusters. Take a statistical sample with well-known photometric magnitudes and distances. Take isochrones and theoretical star for evolution. Models based on observations is equal to circular argument. All these methods are not self-consistent and always introduce an unknown error to the analysis. Here you see the fraction of OF main sequence stars type earlier than SPD. For example, here we see the result of classical spectral classification. For example, 10% of stars with MV is equal to minus 4.5 magnitude are on the main sequence. for BO type stars. Or for example, only 70% of stars with MV is equal to the 2.5 magnitude are on the main sequence for F8 type stars. These values are depending on the chosen sample for the spectral classification and which classification scheme is applied. The errors are rather large. All observations have to be normalized to one standard system, which means essentially to one time scale. The observations show that this heuristic law describes them very well. Theta m is approximately m to power minus gamma, Salpeter law, we call it. Star clusters are one of the most important observational test for the initial mass function because they normally have well-defined age, distances, and metallicities. However, the errors are still quite large, but there is still no homogeneous initial mass function determination for open clusters taking into account the available data. You see here for different organizations, for example, for Salpeter, Blue, for Krupa, for Fabrier, we see they had an argument that whether the gamma is constant or not. And you see for example, for associations, they are different, and also clusters, field, star forming. The gamma is different. Here you see different clusters. We have someone tested for type O2 data for 7 clusters, and you see some of them are young. For example, IC2602, it is 10 million years. It is young, and some of them are old. Persephone, it is 650 million years. It's old, but IC2600 is young cluster, or for example, Alpha pair is young cluster. And the point is the gamma is here. When they measure the gamma, they see there are a lot of large errors. The errors are large, you see, even 1.24. And they try to measure for mass function slope gamma for 2 subregions and for the whole cluster region in the given mass range. For example, they assume a cluster. For example, you can say cluster, the core or inner region, and then a circle near the center. And then the outer region or the whole cluster then, and they see the errors is for some of them is high, and also in some of them it was good for numbers, but for some of them the numbers are so much different from each other. You see it is for example the minus 0.89, and here it is minus 2.10, minus 1.88. The numbers are so much different with each other. Here we have genes length. When does gravity win? N molecules of mass m in a box of size L. Just pay attention that do not confuse with the luminosity. L is related to length for genes length. At temperature T, we have gravitational energy minus g m squared L over L. thermal energy NKT, total mass Nm, the ratio of gravitational energy over thermal energy, and Jean's length, and then gravity wins when L length is larger than Jean's length. Jean's length, you see here, Jean's mass, and at last we can say the lowest Jean's mass is for cool and dense clouds. You see here the star formation, the stage of star formation. First we have molecular cloud, and then we have a core. That core collapse, and then we have magnetic field, and then we have shock wave, and then we have rotation, protostar. Maybe it is because of the rotation is because of the shock wave, or some star pass through this way, or jets. So at last the rotation happened, and then we have gas outflow. There are jets, we have star, we have disk, as you see here, protostar. Star formation, the detection of free gas in a star cluster is an excellent indicator for the time scale of continuous stellar formation. Star formation lasts 3 to 4 million years and is continuous. This is also the intrinsic error of an age determination. Numerical simulations of star formation in giant molecular clouds. Hypothesis is the formation of all members of a star cluster is continuous for 3 to 4 million years within one giant molecular cloud. Is this a realistic approach? Is it possible to simulation the formation of star clusters and compare the results with observation data within the solar vicinity? And here you see for example, for basis Orion Nebula and Taurus star formation forming region, complete astrophysical numerical simulations including shock waves, dynamical parameters, and 3D hydrodynamic, Jean's mass less than 1 solar mass, and the numerical simulations are astonishing close to observations. Input parameters are mass for giant molecular clouds, 50 solar mass limited by CPU time. Diameter is 0.375 parsec, limited by CPU time. Time for the gravitational collapse, 19,000 years. Random turbulence field with a 3D Gaussian distribution. Here you see the star's mass is larger than 0.084 solar mass. Brown dwarf mass is less than 0.084 solar mass. It has no hydrogen burning. For more low mass stars formed due to the initial mass function, we can say that we have more low mass stars formed due to the initial mass function. For star clusters, it is essential to know the internal velocity distribution because of their evolution. And you see here the number of stars formed for core, initial gas mass, solar mass, initial size in parsec, and final gas mass in solar mass, and number of stars formed, and number of brown dwarf formed. mass of stars and brown dwarf, and star formation efficiency in percent. And we can say that there is a continuous star formation time. As you see, we have the star formation is now continuous. Here is the formation of binary stars. In here, the root mean square of velocity distribution dispersion of the simulations is 4.3 kilometer over a second. Such observations data for D is larger than diameter is larger than 500 parsec are still not available. Gaia satellite mission, which we calculated. Binaries are connected with the line you see. These are binaries. Magnetic field star formation. You see here the effects of magnetic pressure on fragmentation. Here, increasing magnetic field strength. At first, for example, we didn't have any magnetic field. As time went by, you see the magnetic field increases. And we have here a lot of magnetic field. Also here, it is the increasing magnetic field strength. And also here. You see the magnetic field. Also here, and that it produces a star. Evolution of star clusters. Star clusters form with the following characteristics. 1. Total mass, initial mass function. 2. Metallicity. 3. Kinematics of the cluster center location within the galaxy. And 4. Internal velocity dispersion. And how does the star cluster evolve with these starting parameters? We will answer it. Each member or each star evolve as an individual some important topics. Binary evolution, mass loss, hot stars, AGB evolution, planetary nebula or cool stars, supernova explosions. In star clusters, collisions are very uncommon. Almost no new multiple binary systems formed during the later evolution. Star clusters normally follow galactic rotation. You see the star formation. For example, if we have a massive giant molecular clouds, then we have blue supergiant, and then we have supernova, and we have supernova type 1 and supernova type 2. And then you see this is the decrease in the mass for the proton star. For example, for Sun, we have proton star and then sun-like star, red giant, planetary nebula, and then white dwarf. And at last, with a very, very low mass in giant molecular cloud, we have proton star with a very low mass, and then we have brown dwarf, and then at last it is again brown dwarf with a lower size. Thank you for your attention and see you next time. Bye.